You stand on solid ground, held firmly in place. An apple falls from a tree, undeniably pulled downwards. This force, gravity, seems so simple, so intuitive. It pulls everything towards the center of the earth, right? But what if that's not quite right? What if gravity doesn't actually pull at all? For centuries, humanity looked up at the stars and down at falling objects, convinced of this invisible tug. But a revolutionary idea, born from the deepest corners of the universe, completely redefined gravity, showing us it's not a pull, but something far stranger. And once you understand it, the cosmos will never look the same again. For thousands of years, the concept of down was inextricably linked to the earth. Aristotle, the intellectual titan of ancient Greece, believed that objects had an inherent tendency to seek their natural place. Heavy objects like rocks belonged to the earth and moved towards its center. Lighter objects like smoke belonged to the heavens and moved upwards. It wasn't a pull in the modern sense, but an intrinsic desire of matter to return home. This elegant, albeit incorrect philosophy dominated thought for almost 2 millennia, shaping how humanity understood its place in the universe. In this Earth-centric view, the cosmos was a series of crystalline spheres, each carrying a planet or star, rotating around us. Everything had its place. The idea of an invisible force reaching out and pulling objects across vast distances wasn't really considered. Motion was either natural, like a rock falling, or violent, like an arrow shot from a bow. But even for violent motion, Aristotle believed the air behind the arrow pushed it forward. There was no need for an abstract, unseen pull connecting disparate objects. The universe was orderly, predictable, and fundamentally centered on Earth. Then came Galileo, challenging the very foundations of this ancient worldview. His observations of Jupiter's moons orbiting Jupiter, not Earth, shattered the geocentric model. He also conducted experiments on falling objects, famously demonstrating that objects of different weights fall at the same rate, contrary to Aristotle's claims. Galileo realized there was something consistent, something universal, about the way objects accelerated downwards, but he didn't quite crack the why. He observed how things fell, but the force behind it remained a mystery. Enter Isaac Newton. The story of the apple falling on his head, whether literal or apocryphal, perfectly encapsulates his eureka moment. Newton didn't just see an apple fall, he saw the moon orbiting the earth, and he connected the two. He asked the revolutionary question: is the same force that pulls the apple to the ground also responsible for keeping the moon in orbit? This audacious leap of imagination was the spark that ignited a new understanding of the universe. Newton envisioned a cannonball fired from a tall mountain. If fired with enough speed, it wouldn't just fall to the ground, it would fall around the earth, continuously missing the surface. This was the same principle, he argued, that kept the moon in perpetual orbit. The moon was constantly falling towards Earth, but its sideways motion was so great that it kept curving around the planet instead of hitting it. This was gravity in action, but it needed a mathematical framework. Newton formulated his universal law of gravitation, a groundbreaking equation that described gravity as a force of attraction between any two objects with mass. The more mass they had, and the closer they were, the stronger the pull. It was a magnificent achievement, explaining everything from falling apples to planetary orbits with astounding precision. Gravity, for the first time, was not just an observation, but a quantifiable, universal force, described as an invisible pull, acting across empty space. This action at a distance, as it was called, was perplexing. How could one object instantly influence another across millions of miles of empty space without any physical connection? Newton himself admitted he didn't know how gravity worked, only that it worked and how to calculate it. He described gravity as a force, a pull, but the mechanism remained elusive. It was an invisible hand reaching across the void, an almost magical interaction that defied common sense, yet perfectly matched observation. For over 200 years, Newton's gravity was the undisputed champion. Newton's gravity painted a picture of a clockwork universe, predictable, mechanical, and governed by precise laws. We could calculate the trajectories of planets, predict eclipses, and even discover new planets based on their gravitational influence on existing ones. It was a monumental triumph of human intellect, providing an almost complete understanding of celestial mechanics. But even in its perfection, a nagging question lingered. What is this pull? Is it truly a force acting through nothingness? The first cracks in this beautiful Newtonian edifice appeared in the late 19th and early 20th centuries, specifically with the orbit of Mercury. Newton's laws predicted Mercury's orbit almost perfectly, but there was a tiny, persistent discrepancy that couldn't be explained. It was like a single cog in the cosmic clockwork was just slightly off. This tiny anomaly suggested that something fundamental was still missing from our understanding of gravity. And then a young patent clerk named Albert Einstein stepped onto the scene. Einstein began with a thought experiment. Imagine you're in an elevator in deep space, far from any stars or planets. If the elevator cable starts pulling you upwards, you'll feel pressed to the floor, as if gravity is pulling you down. Now, if you can't see outside, how do you know if you're accelerating upwards, or if you're just standing still on Earth, feeling Earth's gravity? Einstein realized there was no way to tell the difference. This simple equivalence between acceleration and gravity was the key. If acceleration and gravity are equivalent, and if light travels in straight lines in accelerating frames, then light must also bend in a gravitational field. This was a radical departure from Newton, who believed gravity acted on mass, not massless light. This prediction was testable. It meant that a massive object, like the sun, could literally bend the path of starlight as it passed nearby. The universe was starting to reveal a more complex character. But this still didn't explain how gravity worked, only its effects. Einstein's greatest insight was yet to come. He realized that Newton's action at a distance was a misconception. Gravity wasn't a force acting within space, but rather a manifestation of the very structure of space and time itself. He saw space and time not as a static backdrop, but as a dynamic, interwoven fabric. Space-time. Imagine space-time as a stretched rubber sheet. Now place a bowling ball in the middle. What happens? It creates a dip, a curvature in the sheet. If you then roll a small marble nearby, it won't move in a straight line. It will curve inwards, following the contours of the sheet, drawn towards the bowling ball. It's not being pulled by the bowling ball, it's simply following the shortest path in the curved geometry of the sheet. This is the essence of general relativity. In this revolutionary view, massive objects like planets and stars don't pull us. Instead, they warp the very fabric of space-time around them. Think of it. Earth isn't pulling the moon. The moon is simply following the curves and valleys that Earth creates in space-time. When you drop an apple, it's not being pulled to the ground. It's following the shortest, most efficient path through the space-time curvature caused by Earth's mass. It's like rolling down a hill, but the hill is an invisible distortion in reality itself. This curving of space-time doesn't just affect motion, it affects time itself. Einstein predicted that gravity slows down time. Clocks tick slower in stronger gravitational fields. This phenomenon, known as gravitational time dilation, has been experimentally confirmed. GPS satellites, for example, have to account for it. Their clocks tick slightly faster in weaker gravity higher above Earth. And if not corrected, our navigation systems would be off by miles every day. The crucial test came in 1919 during a total solar eclipse. Astronomer Arthur Eddington led an expedition to observe stars whose light passed near the sun. According to Newton, their light should travel straight. According to Einstein, the sun's immense mass would curve space-time, bending the starlight and making the stars appear in a slightly different position. The results were clear. The starlight did bend, exactly as Einstein predicted. The world suddenly realized that Newton's pull was actually space-time's warp. Einstein's theory also predicted the existence of gravitational waves, ripples in the fabric of space-time, much like ripples on a pond, caused by violent cosmic events like colliding black holes. For decades, These waves were purely theoretical. Detecting them would be incredibly difficult, requiring instruments sensitive enough to measure distortions smaller than an atom. But in 2015, after decades of painstaking work, the LIGO experiment finally detected these faint echoes of colliding black holes, confirming yet another incredible aspect of general relativity. So, when an apple falls, it's not being pulled by some invisible string. It's simply taking the path of least resistance through the distorted, curved spacetime created by the Earth's mass. The Earth isn't pulling you down, it's curving the ground beneath your feet, and you're simply following that curve. It's a subtle but profound distinction. Gravity isn't a force that reaches out, it's the geometry of the universe itself, telling matter how to move. This shift from gravity as a pull to gravity as a warp isn't just an academic detail. It completely reframes our understanding of the cosmos. It explains black holes, where space-time is warped so intensely that nothing, not even light, can escape. It underpins our models of the Big Bang and the evolution of the universe. It shows us that reality isn't just a stage upon which events unfold, but an active participant, shaped and reshaped by the matter and energy within it. We started with Aristotle's natural place and Newton's invisible pull, but the journey through Galileo, Einstein, and countless others has revealed a universe far more intricate and beautiful than we could have imagined. Gravity isn't some external force tugging at objects. It's an intrinsic property of existence, woven into the very fabric of space and time. It's the universe shaping itself, guiding the dance of galaxies and stars, and keeping your feet firmly on the ground, not through a pull, but through a curve.